Yes, hello everybody. Thank you, Bika, for this introduction. So, everybody, hello. So my name is Zain Saad, and this presentation has been developed and achieved with my colleague Sébastien Denetière. We are both work in RTE, so it deals regarding, it's about EMT modeling and simulation of the CIGRE B4 DC Grid. So the context of this work, it was started in 2011 when CIGRE B4 study committee initiated several work groups on DC Grid. So in order to organize the discussion among the groups, it was decided to develop a VSC-based DC Grid test system with AC and DC system with all input data. So basically this test system has been shared among all the DC Grid working groups, so it is publicly available, and actually the aim here is to provide, I would say, the first DC Grid benchmark to be used for a research community and engineering community. So it is used basically to perform DC Grid systems study some issues as the protection issues, the load flow, DC load flow, dispatching studies, transit stability, reliability, and etc. So this is, I would say, a huge DC Grid system that is, this is used for research studies. Okay, so for the scope of this presentation, this one will present the EMT modeling and the simulation result of the Cigré B4 DC Grid test system. This DC Grid was developed and used for the working group B457 and B458, and the VSC station is based on the Modular Multilevel Converter technology. So this is the Cigré DC Grid test system that was developed in this working group. So I would go through, I will give a brief description of this grid. So basically, as you can see, you have, it's quite big. You have around 11 converter station and 16 MMC station converters. So of course it's not realistic, but it's still used. The aim of this grid is to do research and engineering studies for future.
We can't see your screen.
Do you see my screen?
No, not yet.
No? Oh.
On the top panel, it should be a play button. There we go. Thank you.
Okay, sorry. So is it correct now? Do you see the screen? Yeah.
Yes, very good. Thank you.
Okay. So I think you did not miss a lot of I would say figures. So there were no figures previously, so it's fine. So this is the grid. So as I was saying, it's a big DC grid. So the main description, it's mainly done with a two onshore AC system, as you can see here. So this is the red area. So you have one AC system here, one AC with a AC voltage of 380 kilovolt. Then you have four offshore AC system here, which will represent wind farm or oil platforms. And then you have a 3 DC system. So you have the first one, which is a DCS1 called, and then you have a second one, which is with 6 terminals, and then you have the third one, which is the DSC2 here, which is blue light. So the dark blue is a DC system with a plus and minus 400 kV, and with a light blue, so here and here, it's a DC system with a plus and minus 200 kV. Okay, and so each station here is represented. It's a monopole or a bipole. I will explain what is the difference between monopole and bipole. So basically you have 6 monopole stations and you have 5 bipolar stations. So this is the main idea of the system. So so the question is, how do we model this DC grid in EMT software as EMTP, PSCAD, HyperSim, or RTDS, etc. So this is how it's been made in EMTP software. So basically the DC cables, AC cables, DC line and AC line are developed using the frequency-dependent line and cable model, which is provided with all the EMT software tools. The MMC converter is quite complex, so we're using here the detailed model, and basically you have 4 types of model that were being used depending of the study you want to do. Then you have the DC-DC converter. What has been decided in the working group is to use the idle transformer, since this device is not yet available. So the working group decided to use the idle transformer with no impedance. So just to have voltage differences between both terminals. And then the AC equivalent is basically a small voltage source with RL impedance, and the load is used, we are using simply a RL impedance linear component, I would say. So this is the converter station configuration. So as I mentioned previously, it's made using the MMC topology. So the main idea of the topology is provided here. So you have several submodules connected in series. A group of submodules represent one valve or one arm, and at the end you will end up with 6 valve or 6 arm, and each 2 arms are connected to the AC side. So basically you will have at the end 6 arms, and then you have a star point reactor, which is used to have a reference to ground, and then you have a transformer step up transformer to connect the AC side to the converter terminals. Okay, of course you have also startup insertion resistance, what we call here. This is used only for the startup sequence of the converter. So basically, what happens is that during the startup, the switch here is open, and the resistance will be used just to limit the inrush current and to charge the capacitor, and then at the end of the startup sequence we will switch the switching to bypass the resistance and go to normal operation. Okay, so as I mentioned, you have monopole and bipole configuration. So this is the difference between both. So monopole configuration use one MMC converter with a startup sequence with a start point reactor to have reference to ground. Because you don't have any reference to ground on the DC side. And then the bipolar configuration, in this case you have 2 MMC, you have 2 transformer, and then you have the grounding, which is on the DC side in this case. So in this case you don't need the start point reactor. So this is the MMC model that are used, that were presented in the working group and are used in the MTP model. So basically you have 4 types of models that are available. So the main idea here is that, as you can see, from model 1 till model 4, the model 1 will be the most detailed, and the model 4 will be the most simplified. I would say the model 4 will represent a model close to the phasor domain software. So this is how we model the MMC, and of course each type of model will have simplification, as you can see here. So the black box here represent the simplification made at each level of type of models. Okay, so in the model 1 represent all the diode, all the IGBTs, and then if you go to model 2, you will just have representation of the power electronic circuit, and then you have the model 3, which will represent an aggregation of all the submodules to represent just the arm, and then the model 4 is based basically on the analytic equation similar to phasor domain, and can be used for electromechanical studies, not for EMT studies on the DC grids. So the model 1 and 2 can represent the capacitor voltage balancing, as you can see, since the submodules are represented. So the control of the capacitor voltage balancing should be used to balance all the capacitor, and the circulating current suppression. In the model 3, since the submodules are aggregated, in this case the capacitor voltage balancing is not used because the capacitor is already simplified, but still the circulating current suppression should be used. And the modeling, and for the modeling 4, here you don't have any lower level control. You just need to have a representation of the outer control or the inner control. So this is the structure of the control system used. So basically you have the dispatch control, which will provide, so you have 3 steps. The first step has not been used in the working group, but it's developed. So the first step is a dispatch control. So the first one is will provide the reference active and DC voltage reference, and also the reactive power and the AC voltage orders. This order will be sent to the upper level control here. This upper level control will control, has several structures inside. So you have outer control or the inner control. The output of the upper level control will provide the AC, 3-phase AC orders, which will be provided for the lower level control. And the lower level control, you have several control systems, and this output of the lower level control will be the gating signal to fire for the firing pulse of each IGBT. So this is the main structure that is used in this model. So some ideas, just a small recall of the main structure of this different controls. Okay, so let's start with the inner control. Of course, this inner control is very similar to the classical VSC. So it's made of a DQ reference frame. So we change from ABC to DQ. We have transformation, and then you can use we'll use the ID reference to control the active power, and the IQ to have the reactive power. So this is the idea, and then you have a PI loop, which will, in order to correct the measured values and to settle it to the desired values. And this will provide you the AC voltage references. The outer control here, you have, of course, you have several type of outer control. For the D reference, you have the choice between active power control, DC voltage control, droop control, and VF control. So let's start with the P control. It is shown here. So the P control, you have a loop in order to set up the active power reference. When the station is set as a P control. The DC voltage control, of course, we have also a PI loop. When the station is a VDC control, and then we have also the droop control. So this is a PVDC droop control. So basically, you have this is a control which will balance the DC voltage and the P control as in a droop manner. Okay. And then you have a VF control. The VF control is used basically for offshore AC system as wind farm or platform, oil platform, etc. So this is the basic idea of the VF control. And for the Q reference, you have two choices. You have or the Q control or the VAC control. So you will control the reactive power or the AC voltage control. Then you have the circulating current control. So this control loop is in the lower level control, and this is basically a control which is related to the MMC topology. Usually it is already known that the MMC will generate a negative sequence with a second harmonic. So in order to make it work, you need additional control to control this negative sequence current that will generate losses in the station and also can generate instability. So usually in the HVDC, the usual way to do this is just to eliminate or to suppress this circulating current. You have other type of control system that are more fancy to control this circulating current. But in this working group, we decided just to go with a simple control, as it's shown here. So the EDIF is the circulating current control. So this is differential current, and when you write the equation, you will end up with 2PI control. And of course, as I mentioned, in this case, the circulating current reference control are set to 0. So the reference are set to 0. So in this way, we can achieve zero circulating current control, zero circulating current in each phase of the MMC. Then you have also the NLC modulation. So this is the objective of the NLC modulation is to transform the AC reference to a number of inserted submodules for each arm. So it's shown here. So we have the AC reference provided from the inner control, and then you have we'll use a simple round function multiplied by the number of submodules in each arm, and you will end up with the number of submodules that should be inserted to respect the reference voltage. So at the end, if you have a reference voltage equal to 2, here we have a BS of 1 per unit because it's the arm voltage, it's not the AC voltage. So this means that you need to insert the total number of submodules in the relevant arm. Okay. The balancing control algorithm, this is the last control system that is used, and the aim of this balancing control is to balance each submodules of each arm. Okay, so so here what we'll use is that you will need the number of inserted submodules. So it's connected to the NLC. You need the current, measure the current of each arm, and then you need to measure the voltage, capacitor voltage of each submodules. And by doing some sort function, you can check which capacitor voltage of each submodule are the highest, and then you can balance if the current is positive or negative. So when the current is positive, we will insert the submodules that have the lowest voltage capacitor voltage, and when the current is negative, you will have to insert the capacitor voltage that have the highest capacitor voltage in order to discharge and charge. So by doing at each time step this process, you will end up with a balancing of all the capacitor voltage of each arm. Okay, so this is the main idea. And the output of this system is the switching and the gating signal, which will go and commutate each submodules. So the protection used also, now the protection it's very simple. Okay, of course in real world it should be much more complicated, but here we keep it simple since it is a benchmark. So the main two control, it's one from the AC side and one from the DC side. We basically measure the AC voltage at the primary side and the PCC, and we check if it's lower than 0.1 per unit, then we block the converter. Okay. Otherwise, the converter will manage the fault. So this protection is for three-phase fault, and for DC fault protection, here we will use only the IDC current. We will measure the IDC, the DC current, and then you have a threshold. And if this threshold is exceeded, then you will block and open the AC breaker. So we will block and trip the converter. So of course, we added also some delay, artificial delay, to take into account the delay that can occur in the mechanical switch. Okay, so here we are using 40 milliseconds. So when we send a delay, when we send a trip, it takes 40 milliseconds before it really opens the AC brake. Okay, and also for the blocking of the MMC, we estimated we are using a 40 microsecond artificial delay between the protection detection and the sending, the real sending of the signal. So what is the challenge to simulate the test system in the MTP? Of course, as you can see, the main circuit parameter, you have 16 converters because you have 5 monopole. Yeah, you have 6 monopole and you have 5 bipole, so you end up with 16 converter, MMC converter. So of course you have all the 16 control, and then you have also the line cables, which is we have 23 frequency dependent line cables. So all this, of course, will increase the simulation time and make it a little bit complicated. So the total number of this DC grid, when you compute the total number of nodes, in this grid, you will end up with more than 40,000 nodes, which is quite relevant. During the working group B4 57, so we have decided to work as follows. So we started with the first step. We did the model in EMTP, and then we used another software to make sure that the results are accurate and that the same result can be provided with other software. So we use PSCAD and EPRSIM to validate the MTP model that has been done. So of course these models are available, publicly available, so the MTP, PSCAD and EPRSIM, and it is, as I mentioned previously, it is made available for the public to use it for research study, etc. So this is the MTP-RV model used. Okay, so as you can see, it's very similar to the first figures. So you have the DCS1, sorry, and then you have DCS3, DC Grid here, and then you have the DCS2, and then of course you have the voltage source, the AC side here, the offshore AC system at this side, and this station, for example, is considered the oil platform. Okay, so in this model, the blue color of the station represent the control used. Is it a P control, DC voltage control, PVDC, or VF control? Okay, so here just the P control is used for the green color. So whenever you see green, it's a P control. When I see a VDC voltage, DC voltage, it's the cyan color, etc. Okay, so you can see that here the pink one is the PVDC droop control. You have droop control. You have VDC control here, and here you have P control, and here you have a VF control. Okay, so the time constant of the auto control is 90 milliseconds. Yeah, this is what has been decided. So let's start with the first transit test case used to validate this model. Of course, this step has been made after validating the load flow simulation. So we make sure that the load flow is converged and is accurate enough, and then we start to perform simulations. So in this test case used here, we assume that the CBA1, so this station here, is tripped at t equal 1.5 seconds of simulation. So by tripping, I mean that we'll open the AC and DC breakers. So we'll suddenly open it, and the purpose of doing that is to lose power in the DC grid and to see how does the other station will react on this disruptions. So here, of course, this is a station which controls the VDC. So when you use a VDC, what do we expect? We expect that the P control here, since it controls the P control here, it will not change, it will not have any effect. And here, when you have a droop control, PVDC, in this case, this station will drop because you will lose some power here. So this one will automatically adapt as a primary control to adjust the VDC respect to the active power. So as we will see to the next slide. So this is the result. Of course, since you have 11 terminals, you have a lot of data to see. You have a lot of data to analyze. So which is a little bit sometimes complicated because you can have just by plotting the active power, you will see that you have a lot of variables to see. So here we are showing the active power, and then here we are forming the DC voltage at the plus and minus 400 kV and the DC voltage of the plus and minus 200 kV. So what's happening here? So let's start with the green one. This is the station that is tripped. So this one is tripped, so it goes from 1,600 megawatt, goes suddenly to 0. So as I mentioned before, since you have a droop control in your system, this station here, you see that they will automatically adjust their active power in order to compensate this power loss here. Okay, so you can see that the CBB1 and CBB2, so this one and this one here, they will suddenly they will act as an active primary control to adjust the active power. Okay, and however, let's say this CBD1, you see that it stays constant. You have some slight disruption, but at the end it stays constant. Okay, so you can see some kind of result. Other comment I can say here is that the outage is made at 1.5 seconds, and you can see that it is less than 300 milliseconds at 1.8 seconds here. You can see that in less than 300 milliseconds, the DC grid is already stabilized, so it's quite fast. Okay. On the DC voltage, you will see some transit. These transits are related, of course, with the cables, lines, combination of cables, combination of lines, and also with the impedance, frequency impedance of the grid of the station. So you can see some harmonic here, which is quite predictable. Okay, you can see here some harmonic, but still at the same time you can see that the system is still stable. Okay, and the DC voltage here will drop. Why? Because we lost the VDC control, and what is remaining is the droop control, which will reduce the DC voltage in order to manage the active power. So this is a droop control effect here. Okay. Here, however, you can see that this DC voltage, which is related with B1C1. So B1C1 is this one here, is this bus. And you can see that since we trip this one and this grid DC system is separated from the other one, of course this system should not be affected from the loss of this one, because it's not connected on the DC side. And what is already shown here and what you can see it here. So the B1 MC1, the voltage, DC voltage, is already maintained at its values here. Okay. Otherwise, the other voltage here will droop because they are rated in the same DC grid system. Okay. Here is some figures to show you the validation of the model 1, 2, 3. So as I mentioned, you have 4 types of MMC model. And so we performed this simulation with the 4 type. But what we are focusing here is mainly the 3 first models. So 1, 2, 3. I will just give you a small recall on this. So this is what we are showing the result of model 1, 2, 3 here. Okay. Let me go back to the slide. So yeah, as you can see here, it's quite accurate. Okay, the 3 models are quite accurate. Why? Because we are doing some transit on the DC side, and for this type of transit, you can see that the model are accurate. So it's quite good. For the model 4, you can have some discrepancy that we did not show here, but usually the model 1, 2, 3 are used for this kind of studies in DC grids. Here is another results between model 1, 2, 3. So in this case, for these studies, all these 3 type of models can be used. Okay. So this is another transit test case used also to validate the model. In this case, we are performing a DC fault here. So it's a pole-to-pole fault. This is an extreme case, of course. So we are performing a DC fault at around 1 second, and then actually we assume that it stays for 3 milliseconds, and then it disappears. Okay, so it's I would say fugitive DC pole-to-pole fault, which is quite correct because this is a DC line. So we can expect that DC lines can have fugitive DC pole-to-pole fault, which will stay for 3 milliseconds. Okay. So this is let's start first with the protection activation of each station. So here you have an example, okay, to see when you have a DC fault at this point, what is the time required for each converter before he trips. So of course, so let's start. So since the DC fault is at the BB1, the first thing we can expect is that the CBB1 should be the first one to trip, and the first one the protection will detect, of course, because this is the closest station. So as we can expect, you can see that this is the fastest one. So whenever, if we go a little bit further than the DC fault, so you have DC fault here, and if you see what happened on the CBA1, since you have a line here, so this one will trip a little bit later, so it's 2.12 milliseconds, which is a little bit later. And if you go further at the BBD1, CBD1 here, which is a little bit further at the remote than the DC fault, so you can see that the time of the tripping is a little bit longer and longer. So here we are imagining that if the DC fault remained for 3 milliseconds, what will happen is that only the converter in CBA1 and CBB1 will trip, and the remaining here will still be alive, I would say, will not trip. Okay. So this is the result, as I mentioned previously. So this is the active power result. So you can see that the pink one, this is the CBB1, so this one will trip, and the remaining converter can fault right through this DC fault. Okay, as you can see. So you can see that all the remaining are still active. Okay, and of course, as we lost two converter stations, so we lose power, and in this case you have the other station which will adjust automatically their active power to balance the loss of power in the DC grid. Okay, you can see here some transit DC voltage transit. Of course, you have a lot of harmonics. This is due to the wave propagation of the cables, lines, combination of cables, lines, and also the station, including the station, etc. So it's getting quite transit here. You have a lot of transit at this stage. So once again, we validate. Here we are showing the results of comparison results of model 1, 2, 3. So you can see that even for this type of fault, which is quite transit, the 3 type of fault models gives accurate results. They are quite good. So I would say that the model 3 and model 2 are very close to the model 1 for this type of test. So so now I'm showing you the time domain simulation, the simulation computation time needed for this studies. So I'm comparing the model 1 with the model 2 and model 3. So for 1 second of simulation with a time step of 20 microseconds, of course, the model 1, since it's the most detailed one, you should expect around 3 hours to do the simulation, which is quite huge, of course. So the model 1 should not be used for studies. It should be used just for validating simplified models. Okay, this is not a model that you use for studies. You just need to use it a very few times to make sure that your results are correct. Then you have the model 2, which is around 8 minutes, and then the model 3, which is around 2.2 minutes. So I would say that the model 2 and 3, especially the 3, it's quite fast to do such simulation in EMT simulation. So this is the conclusion. What I show you is the Cigré DC Grid, including the 16 MMC stations. Modeling details and simulation results were presented. The dynamic behavior of the DC grid control is fast. As you can see, it's quite fast, less than 300 milliseconds. For DC fault, as the DC fault dynamic is very fast, then the projection should be also fast in order to be enough robust and selective. And you can see that everything on DC side is quite fast. So even the station should be quite fast to respond to such kind of DC fault. Computation time are reasonable for the time domain simulation, especially for model 2 and especially for model 3. So model 3, as I mentioned, gives accurate result in this test case, but please do not remember should be validated for other test case where you can have differences. So this validation is not sufficient to say that model 3 is quite accurate for all studies. Okay, but in this case it's quite good. And produced in several commercially available EMT simulation as EMTP. And thank you very much. So if you have any question, I'm now you can answer our questions.
Looks like we have 2 questions so far.
Just going to. Okay, so I will start with the first question, which is more general. Will this presentation be online? So I imagine yes. It will be available on the webinar after.
Yes, this presentation has been recorded.
Okay, so another question from Wei Xingling. So this question is regarding in the DC fault simulation, the DC voltage increased up to 1,000. Do cable line allow such high voltages? Which is a quite interesting comment. Of course, in this, yes. So I will go back to the result just to explain for everybody. I think it's DC fault. So, so yeah, the participants were asking about this over voltage here, the DC voltage, which will increase from 8 kV to 1,800 kV. This is a big issue, of course. Usually in a converter station, they include the surge arrestor, which should limit this over voltage shown here. So if in the DC Grid benchmark was including in this DC Grid benchmark, we did not include the surge arrestor. So this is why you have a huge over voltage. If you have surge arrestor, you will cut out this this over voltage. But of course, it's still an issue to that should be dealt, and this is one kind of the issue that should be dealt in DC systems. So here, what we are providing is a benchmark to see what is the issue that can occur and how do we deal it. So I go to the next question from Wei Xing also. In the projection, why not consider DC current limiting reactor that are associated with DC circuit breakers? Why not consider DC current limiting reactor? Here already also another question from Wishing. Of course, the DCCB are not included in this DC grid. Once again, this is the benchmark, and this is the model used in the working group B4 57 and B4 58. So there were no DCCB in this grid. So no DCCB, no inductance. But of course, once again, this DC grid that should have been was developed in the working group in 2 years. So there is, of course, some limitation. And once again, this is a test case. And all researchers should be available to enhance it and have another better DC system. Thank you so much for your presentation. Okay, so I will go to the third question. Why 20 milliseconds for AC side but 40 milliseconds for DC side fault is used? The delays were not shown and result at different breakers points. So why 20 milliseconds? Yes, I think here there is, it should be, yeah, this is 40 milliseconds. This should be 40 milliseconds since it's 4 seconds. The delay were not shown in the result at different breaking points. So the second question is not so clear. The delays were not shown in the result at different breaking points. Yes, I mean what you are showing here is just the result. So it's just the test case. This is once again this simulation has been made for the working group. So we have decided to use 2 test cases and we did the simulations. Of course, you have a huge number of simulations that we can do with such big DC grids. In the MMC protection, why MMC are blocked when AC voltage is lower than 0.1 per unit? Should MMC be able to ride through zero AC voltage? This is another question from Wishing. Thanks for this other question. He's asking regarding the AC protection here. Why do we use a threshold of 0.1 per unit? This will depend of the AC. This will depend of the requirement, project requirement, of the TSO requirement. Usually in RTE TSO we use 0 per unit, so 0% voltage, residual voltage. But yeah, in this benchmark we decided to use 0.1. We can the user can use a 0 per unit. However, this three-phase protection is not used in this result, so this value will not affect the results. In the MMC protection, why MMC are blocked when AC voltage? Okay, so we have yes. So this is the question. Is respond. Is the model available online? So Mohammed is asking if the model are available online. Yes, of course. The model for EMTP RV, the model is available online. I think he's available on the CIGRE website. Otherwise, you can just send us a mail, and we'll be happy to send you the models, which include this result. So all the models, you have several models, so we are happy to. And I think in PSCAD model also are available, but I'm not sure about PSCAD. I know that EMTPs are available. You can just send me a mail. Otherwise, you can find it on the CIGRE website. So one other question. Why high frequency oscillation observed on DC voltage but not on power? I presume LPF have been used for powers, and did you show actual DC voltage? So Masood is asking regarding the result here. I think it's regarding here. So he's asking why do you have transit on the DC side but not on the AC side. Here you don't have any filter neither on the AC neither on the DC side. Okay, so this is the first response to your question. The transit here is due to the wave of the cables. If you have transit here, this does not mean necessary. You cannot say that if you have oscillation on the DC side that this exact oscillation will appear on the AC side. It's not directly, we cannot mention this directly like this. The other reason is, if you can see here, this oscillation are between 800 and 600 kV. So I would say that this is low oscillation, so it will due to the inclusion of the inductance and capacitor, it will be filtered on the AC side. Okay, on the AC side, of course, this is active power, so it's using a filter of a sliding period of 20 milliseconds. So there is another question. Hello, Dr. Saad. When you simulated the system with HyperSim, have you done that with real time? I did not. Maybe there was a misunderstanding. Actually, we worked. I did this development only in EMTP RV model, and there was other person in the working group who developed HyperSim. So I did not do any HyperSim model of this DC grid. So I did just perform an EMTP. So for this question regarding HyperSim, I think that you can ask one member of the working group, which his name is Philippe Delahaye. I can send you his mail. So you can just send me a mail, and I can provide you his address, and you can he can share. He will be happy to discuss about the HyperSim model of this DC grid. If you run the simulation for different models in PSCAD, and what? Okay, so another question. If you run the simulation for different models in PSCAD, and what was the simulation time in that software? Once again, I use EMTP-RV. I am not the person who developed the PSCAD model. So The control of, so I go to the last question. The control of MMC connected to wind farm are peak control or AC voltage control. Yes, this is a good question. For the wind farm in this, yes. The question is regarding the offshore. Why is this station are in peak control? Here, once again, this is the limitation of this DC grid, but that we decided in the working group to use just a peak control, as wind farm are used as just as a Thevenin source with a low impedance. So we are using peak control here, but we have already developed another version of this DC grid, which include also the wind farm here. And in this case, of course, this station are not in peak control, but are in VF control. So we have another version with a detailed wind farm, okay, where you can study interaction between wind farm here with AC line. And in this case, this station here should be in VF control. So I think this is all the questions. Does anybody has other questions? Okay. I think we are done.
Great, thank you. This concludes our webinar. Our webinar has been recorded